Good evening children, this is Padma from G.k.jain schools. Let us continue with complex numbers from 12th maths. In today's class we are going to see about geometry and locus of a complex number. We shall move on to the topic now. Let us see what is called geometry and locus of a complex number. You can see from the definition it is nothing but the geometrical representation of a complex number in the organ plane, and we will see what is called locus also. And this example sum is similar to the equilateral sum what we did in the previous class. Now we will see the definition of a circle. A circle is defined as the locus of a point which moves in a plane such that its distance from the locus point, that the fixed point is always a constant. The fixed point we call it a center, and the constant ratio is nothing but the radius. Okay, the equation of the complex form of a circle is nothing but x minus modulus of z minus zn is equal to r. If it is less than r, the points are interior the circle, and if it is greater than r, the points are exterior of the circle. And we will see certain example sums and also this exercise 2.6. Example 2.21. Obtain the Cartesian form of the locus of z in each of the following cases. Okay, so we'll see the first subdivision. Listen carefully. This exercise is very important. Most of the 5 marks in complex number might be asked from this exercise, and also the examples. See here, it was given that modulus z is equal to modulus of z minus I. So it was the given statement, and now in all these kind of sums, our assumption for z will be z is equal to x plus iy. Z will always take the value x plus iy. So wherever z is there, I will substitute, replace it by x plus iy. See, x plus iy is equal to x plus iy minus I. Then the next step what I will do is I will group the real parts and imaginary parts. So here there is only x and iy, one real part, one imaginary part, so leave it. And here x plus iy I, so I will take the I outside, y minus 1. So now I will work out the modulus. Modulus means squaring. So x square plus y square, this will be x square plus y square. I have to square this, so a minus b the whole square, that is a square b square and minus 2ab, so minus 2y. Now then I'll square it. Squaring it means this square root will go off, so I'll get it to be x square plus y square is equal to x square plus y square minus 2y plus 1. When I'm bringing everything to this side, this x square and y square will get cancelled. So the answer is 2y minus 1 equal to 0. Now see the second subdivision. Modulus of 2z minus 3 minus I equal to 3. So here also the assumption is z is equal to x plus iy. Wherever z is there, I will replace it by x plus iy. So 2 into x plus iy minus 3 minus y equal to minus I equal to 3. Now I will multiply it inside, makes it 2x plus I2y minus 3 minus I. Now this 2x and I and 3 minus 3 are real part, so I have written them together, 2x minus 3, and my I2y and I are imaginary part, so I into 2y minus 1 is equal to 3. Now the next step I'll do is taking modulus, that is square root, squaring them, and then when I'm squaring, I'm having a minus b the whole square formula. So 4x square minus 12x plus 9, 4y square minus 4y plus 1 is equal to 3. Then once again I'll square to take rid of the square root. So I'm getting it to be 4x square plus 4y square minus 12x minus 4y plus 10 equal to 9. And this time, because when I'm squaring, this 3 will become 9. So I have taken this the other side. So I have got the answer to be 4x square plus 4y square minus 12x minus 4y plus 1 equal to 0. Now we are moving to the exercise 2.6. We'll see the first sum. This sum is a 5 mark sum. If z is equal to x plus iy is a complex number such that modulus of z minus 4i plus z plus 4i equal to 1, show that the locus of z is real axis. That is, when I am doing the locus of z, I should get only real number. Okay, that is the concept here. That is real part. I should get only real part, not real number. So consider this. They have given this to be, that is modulus of this is equal to 1. So let our usual assumption, let z is equal to x plus iy. When I am having this mod z1 by mod z2, shall I split the mod? So mod z1 by mod z2, shall I write like that? So I have written like that, mod z minus 4i by mod z plus 4i. Then I am cross multiplying, and again I am substituting my z as x plus iy in both the terms. So x plus iy, here also x plus iy. Then I will group the real part and imaginary part. So x, this is I into y minus 4, and this is x plus I into y plus 4. Now what I will do, I will take the modulus, that is square. X square plus y minus 4 the whole square is equal to x square plus y plus 4 the whole square. Now what is a minus b the whole square? A square plus b square minus 2ab, and here it is a square plus b square. So a square plus b square plus 2ab. Now see, this x square will get cancelled, y square will get cancelled. So I am having minus 8y. This plus 8y, when it go to the other side, it is also minus 8y. Again 16 and 16 will get cancelled. So minus 16y equal to 0, which means y is equal to 0. So from this z is equal to x plus y, giving y equal to 0, which is nothing but z takes the value what? X plus iy. See, z is equal to x plus iy. When y is becoming 0, z obviously takes the value x. And what is x? Real, which is in the real axis. So we have proved it. Now the second sum, if z is equal to x plus iy is a complex number such that imaginary part of 2z plus 1 by iz plus 1. See, when you are reading these questions, you have to be very careful which is I and which is 1. You should be differentiating what is I and what is 1. Otherwise, no, it will be a confusion. Show that the locus of z is this. Okay. So given imaginary part of, that is, when I am going to solve this expression, whatever answer I am going to get, in that the imaginary part alone is equal to 0. That is what it conveys. Imaginary part of this expression, when I am going to apply z as x plus iy, and after my substitutions, whatever expression I am going to get, the last step, no, that expression, in that expression I have to equate the imaginary part to be 0. Okay, let's see. So 2z plus 1 means in the place of z I will substitute x plus iy. So 2x 2iy plus 1. So I will group the real part and imaginary part. Similarly, iz means I into x plus iy. So I into x, I into I square, then this one, then real part, imaginary part. Now it is 2z plus 1 by iz plus 1. So whenever I am having the denominator, the complex number, I will multiply and divide by the conjugate. So what is this conjugate? Its conjugate will be 1 plus 1 minus I, 1 minus y, minus ix by 1 minus y minus ix. So in the denominator obviously we will use x plus y and x minus y, that is x square minus y square formula. That is a square minus b square, but here since the I is there, you should be knowing about this concept in complex. So I square takes the value minus 1, that's why it has become plus here. Now I will multiply here 2x plus 1 into 1 minus y. Again 1 minus y into I into 2y, and minus ix into 2x plus 1, and I into I becomes I square, which is minus 1, and 2y into x is 2yx, and already there is a minus, so it has become plus. Now once again grouping the real and imaginary. This is my real, this is also real, so I have written them together. Plus I into imaginary 2y into 1 minus y into plus x into 2x plus 1. Okay, there is a minus sign, and divided by the denominator. Now once again we will go to the question. Now it was given that imaginary part of this expression is 0. I have already told you, after getting the last step we have to equate only the imaginary part. What is your imaginary part here? It is this. So this imaginary part alone equal to 0 means, again the denominator when it go to that side it will become 0. So only I am having numerator 2y into 1 2y, 2y into y minus 2y square, x into 2x minus 2x square, minus x into 1 minus x. So when I am taking everything to the other side, because I could not have minus sign in x square and y square, so it becomes 2x square plus 2y square plus x minus 2y equal to 0, and which is what we have to prove. Hence proved. Okay, so now we will see the third sum. See, in third sum you are having around 2 to 3 subdivisions, and I have done the third subdivision. Rest of the sums you can do it as homework. Obtain the Cartesian form of the locus of z is equal to x plus iy in z plus I is equal to z minus I. That is, modulus of z plus I is equal to modulus of z minus 1. Okay, so we will consider the thing. As usual, our assumption is z takes the value x plus iy. Okay, so wherever z is there, I have to replace it by x plus iy. So x plus iy plus I, x plus iy minus 1. Now grouping the real part, x plus I into y plus 1, x minus 1 into iy. Now when I am taking the modulus, it becomes x square plus y plus 1 the whole square, x minus 1 the whole square plus y square. Now squaring them, what will happen? Square and square root will go off, and I have to apply a plus b the whole square and a minus b the whole square. So I am getting like this. So x square will get cancelled, y square will get cancelled. So I can bring this minus 2x and plus 1 to the other side. Obviously plus 1 and minus 1, and this 2 also will get cancelled. So I will be getting 2x plus 2y equal to 0. Taking 2 common outside, I am getting it to be x plus y equal to 0. Therefore the Cartesian form of the locus of z is x plus y is equal to 0. So this is how we have to do these sums. In today's class, We saw about geometry and locus of a complex number. We went through the example sums. We did certain exercise sums also. Rest of the sums will be continued in the next class. Thank you, children.